following was made as a television videotape. Its purpose is to provide orientation for those teaching the Chem Study course.
The place of organic chemistry in the high school chemistry course has always been a subject of much discussion. Chem Studies feels that organic chemistry is very important, and this is borne out by the fact that two chapters, one, the chemistry of carbon compounds, and the second, biochemistry, are devoted almost wholly to organic chemistry. In addition to that, there are two films, one involving the synthesis of an organic compound and the second involving the mechanism of an organic reaction. But these are really not the true reflection of the emphasis on organic chemistry that we find in Chem Studies. The emphasis in the course is primarily on fundamental principles, and the idea is fostered that these fundamental principles are applicable right across the field, and that we do not have a clear separation and a delineation between organic chemistry and other phases of chemistry. Now, this is a departure from what the usual organic chemistry course in high school has been like. For example, in the older courses, invariably we had a series of reactions presented, an illustration of an industrial installation, and one of the favorites was a catalytic cracking tower, and followed this with a lot of nomenclature. Now, there's nothing wrong with a lot of nomenclature, but this is not a particularly interesting aspect of organic chemistry. It's a formalized, systematic study, and it really has very little to do with chemistry. To capture the excitement of chemistry the way it is practiced today, particularly organic chemistry, I think we should depart from this formalized study and instead turn our attention to fundamental principles. An organic chemist is primarily concerned with the relationship between structure and function. He is interested in how to modify function by changing structure. He is interested in how to predict structure by knowing function and properties. And the two films which have been made are concerned with this primary objective. One of them, the synthesis of an organic compound, shows us how by a transformation we can change the properties of an organic molecule. The second one, the mechanism of an organic reaction, shows us how in detail bonds are made and broken during a chemical reaction. This second film is the one which we are to see now. The film that you have just seen has presented a very old and a very important organic reaction, the hydrolysis of an ester. This is really the way that soap is made and is frequently called saponification. I'm sure we will all agree that soap making is a very important reaction indeed. However, it is legitimate to ask, why did we choose to present this reaction? The hydrolysis of an ester is of sufficient importance in itself for presentation, that is true. But even more important is the desire to present an organic mechanism in detail to show exactly how bonds are broken and how bonds are made and the sequence in which this happens. Now, in inorganic chemistry, although this is occasionally important, most of the time mechanism is not a problem. We are concerned with ionic reactions, we are concerned with ionic interactions, and we do not have to worry about bond breaking and bond making. Although some organic reactions are also ionic, most by far involve covalent bond breaking and making. And therefore, we must learn something about the mechanism if we want a true understanding of the reaction. Which bond is broken and which bond is made. The sophistication in studying the mechanism of organic reactions has increased tremendously over the past few years, and I would like to briefly show how this progression has taken place. For instance, originally, there was no attempt to portray an organic mechanism, and the reaction was merely written as an overall net reaction. No indication of bond making and no indication of bond breaking. The next stage in sophistication was to attempt to present some sort of a representation of what was going on by drawing a square about the reacting groups. For example, if we use the methoxyl group of the benzoate ester and the hydrogen of the water, it would be so illustrated, and one would obtain the products benzoic acid and methanol. However, if one chose to write the square in a different fashion, one would still obtain the same products, for instance, by using the methyl group of the methyl benzoate and the hydroxyl group of the water. One could change the mechanism merely by changing the square. Obviously, this was not a fundamental understanding of what was going on. The next degree of sophistication was reached by using a different atom, for example, substituting sulfur for oxygen and considering the hydrolysis of the corresponding thio, or sulfur ester. We may consider this in either of two ways. In the top reaction, the hydrogen of water and the S-methyl group of the benzoate ester may react, in which case the product is methyl mercaptan. In the bottom reaction, the hydroxyl of water and the methyl of the benzoate group may react, and in this case, the product is methanol. The two compounds, methanol and methyl mercaptan, are easily distinguished. Methyl mercaptan has an unpleasant odor reminiscent of skunks. Methanol is odorless, and therefore to tell which has been the course, one or two, is easy to determine merely by the isolation and odor of the products. The objection, however, can be raised that in this molecule we have substituted sulfur for oxygen, and therefore we have made a fundamental difference. Perhaps sulfur and oxygen are not reacting in the same way. To learn the mechanism with oxygen, we need to have oxygen present, and we do that by using the isotope O18. Now the O18 and the O16 have exactly the same electronic configuration. The only difference is mass, and therefore the mechanism which we determine using the isotope is exactly the mechanism that will pertain under normal conditions. The second factor which we wanted to emphasize in this film is the factor of stereochemistry. Organic molecules are covalently bonded molecules, and as a result they have definite bond angles and they have definite bond distances. This gives them a three-dimensional shape, and that means that in order to react they must have shapes which are suitable for the collision to take place, which is necessary for the new bond to be formed. An example of this, for instance, is in the biologically important system where enzymes react under certain circumstances with other molecules. If the molecule with which the enzyme is to react has a spatial configuration different than the receptor site in the enzyme where it is supposed to react, obviously these two cannot get together and they cannot undergo reaction. So when we are considering the reaction of organic molecules, we must consider not only how the bonds are made and how they are broken, but we must also consider the steric situation to see if the right portions of the molecule can actually come together.
This is a Chem Study film, a production of the Chemical Education Material Study. A common chemical reaction, the hydrolysis of an ester, is occurring in this flask. A great deal is known about the mechanism of the reaction, even though we cannot see the molecules react. Let's look at the mechanism using models. Chemists know that hydroxide ion must collide with the ester to give a particular intermediate, which then decomposes into products. But how do we know this is the mechanism? Well, first we need to know the starting materials. Methylbenzoate is one, the methyl ester of benzoic acid. Let's measure out some of the ester. We then add it to the flask in which we will carry out the reaction. One reactant is then methylbenzoate. The second reactant is a water solution of sodium hydroxide. It too is measured. The sodium hydroxide is then added to the reaction flask. Note that the two reactants do not mix readily. An electric heater is placed around the flask, and the stirrer started to ensure even heating. Prior experiments have shown that a temperature of about 80 degrees is desirable. Since the reactants are almost insoluble in one another, they form two liquid layers. In order for the rate of reaction to be appreciable, we must mix the reactants by increasing the stirring rate. The cloudiness indicates the presence of tiny droplets of ester suspended in the water solution. The droplets give a large area of contact between the water and the ester, and the rate increases. After 3 minutes of reaction, the contents have begun to clear. The final clearing means that a homogeneous solution has been formed. The ester droplets have disappeared. The hydrolysis appears complete. Let's isolate the products from this solution. We add a boiling chip to the reaction vessel and prepare to distill the contents. We distill through a column filled with a metal packing. And find that a constant temperature of 63 degrees centigrade is reached. Under these conditions, a colorless liquid condenses and collects in a graduated cylinder. The boiling point and other properties prove that it is methanol. The other product, which we will find to be benzoic acid, is still in the hydroxide solution. We will now acidify the basic solution. Addition of a strong acid causes precipitation of the benzoic acid. Measurement of the acid added shows all the original hydroxide ion remained after the reaction. Hydroxide ion was a catalyst. The benzoic acid is filtered from the solution. We wash the benzoic acid to free it from excess solution. Quantitative measurements of the dry benzoic acid and the methanol show that 1 mole of benzoic acid and 1 mole of methanol are formed when 1 mole of methyl benzoate reacts. Hydroxide ion was a catalyst. The net reaction then is methyl benzoate plus water gives benzoic acid plus methanol. To investigate possible mechanisms for this reaction, let us use a molecular representation of the net reaction. As we compare the reactants to the products, we see that much of the original structure has been retained. For instance, the benzene ring with its adjoining carbonyl group has transferred intact. Similarly, the methyl group, CH3, has also remained unchanged. But what about the other oxygen atom? Let's examine the possibilities. This oxygen atom in the methyl benzoate could end up in the alcohol molecule by remaining attached to the methyl group. If this happens, the oxygen from the water would end up in the acid molecule. Or the reverse is possible. This oxygen could end up in the acid molecule by staying with the benzene ring. In this case, the water would supply the oxygen for the alcohol. So in the ester, there is one oxygen atom whose fate we do not know. If there were only some way to label this oxygen atom, which we will call the bridge atom, we could also determine the fate of this oxygen atom in the reaction. Fortunately, there is a way to prepare such an ester with a labeled oxygen atom in the bridge position. This is the way it is done. The most common oxygen atom, oxygen-16, has a mass of 16, with 8 protons and 8 neutrons in the nucleus. But we recall that many elements have more than one stable isotope. Oxygen-18 is also a naturally occurring stable isotope with 8 protons and 10 neutrons in its nucleus. Thus the two atoms are chemically similar, but differ in mass. Ordinary oxygen compounds contain only 0.2% oxygen-18. But here is a specially prepared sample of water, 10% of whose oxygen atoms are oxygen-18. Using this as our starting material, we can synthesize an ester in which 10% of the bridge oxygen atoms are the heavy isotope, oxygen-18. In the first step of our reaction, the labeled water reacts with sodium. This forms hydrogen and labeled sodium hydroxide. The labeled sodium hydroxide is then added to methyl iodide. This forms sodium iodide and labeled methanol. Finally, the labeled methanol reacts with benzoyl chloride to form hydrochloric acid and labeled methyl benzoate. This synthesis gives us a sample of methyl benzoate labeled in the bridge position. We will use this mass spectrometer in order to detect oxygen-18. First, a flask containing some ordinary water is connected to a vacuum system and the air pumped out. Then water vapor from the flask is introduced into the spectrometer, where it is ionized and passed through a combination of varying electrical and magnetic fields, then strikes the detector. An electrical impulse from the detector is transmitted to this pen, which moves to the right when ions of each mass strike the detector. The paper moves beneath the pen. There's something. At this setting, ions are striking the detector. And here's something else. Again, ions are striking the detector. This large response must represent a very common kind of ion striking the detector. Let's look at the chart. We see 3 peaks due to mass 16 oxygen ions, mass 17 OH ions, and mass 18 ordinary water ions. No other peaks are seen. Now let's try the water enriched in oxygen 18. Here's the O16 peak. Then the peak due to OH of mass 17. And the big peak due to ordinary water of mass 18. But look, here's something else at mass 19. And again something else at mass 20. Comparison of the peak heights due to the ions containing oxygen 16 with the smaller peaks due to oxygen 18 ions confirms that the sample of water indeed contains 10% oxygen 18. Now let's check the presumably labeled ester. We do not place the ester directly into the mass spectrometer, since the large ester molecule would break into many smaller fragments difficult to identify. Instead, we withdraw a small sample of the ester with a pipette. We then introduce the ester into a quartz tube. As you see, only a drop or two is used. The quartz tube is heated and drawn down. After the air in it has been pumped out and the tube sealed, it is placed in a furnace at 1100 degrees centigrade. At this temperature, the ester decomposes into carbon monoxide and other products, including carbon. As the tube is removed, we can see the black carbon. The carbon monoxide can be transferred into this flask and then into the mass spectrometer for reading. A large peak is observed at mass 28, corresponding to oxygen 16. And another, a smaller peak, at mass 30, corresponding to oxygen 18. The 2 peaks indicate the presence of oxygen 18, as with the enriched water. Therefore, we conclude that we now have an ester with labeled oxygen 18 here in the bridge. With this labeled ester, we are ready to repeat our original hydrolysis. But first, let's review the possible fate of our oxygen atom. You remember it could end up in the acid molecule. Or it could end up in the alcohol molecule. Now let's perform the hydrolysis and see where it does go. The hydrolysis is performed in the same manner as before, but using the labeled ester. The reactants are placed in the flask, which is stirred and heated. The product is distilled to give methanol. Does the methanol contain the oxygen 18? Conversion to carbon monoxide and use of the mass spectrometer gives 2 peaks. That's conclusive. The methanol does contain oxygen 18. What about the benzoic acid? Well, it's washed and filtered, then dried before being converted to carbon monoxide and run in the spectrometer. We find only a single peak and no detectable oxygen 18. The acid does not contain the labeled oxygen 18. We have experimental proof that the labeled bridge oxygen, originally in the methyl ester, goes into the methanol and not into the acid. Thus, the oxygen in the water must have gone into the acid. So we know the fate of each atom in the ester. We will use this information to decide which bonds must break during the reaction. Remember, our end products are benzoic acid and methanol. Let us compare these with our original ester. Notice that this entire group, including the oxygen, remains intact. We assume, therefore, that these bonds are not broken. Our experiment with the labeled oxygen also showed that this group remained intact. Thus, it was not this bond which broke, but must have been this one. But under what conditions did it break? And why was it this bond? Now we recall that hydroxide ion was a catalyst. Let's assume that the hydroxide ion initiates the reaction by attacking the methylbenzoate ester to form this intermediate molecule. The intermediate molecule then decomposes, giving us methoxide ion. Note that the labeled oxygen is attached to the methyl group. Methoxide ion is a strong base and, in the presence of water, will accept a proton from water, regenerating hydroxide ion and forming labeled methanol. So we have discovered a mechanism which is consistent with the location of the oxygen 18 in the labeled methanol. But is the mechanism consistent with what we know about the nature of bond polarity? The ester is an electrically neutral molecule, but within the molecule there are polar bonds. For example, this carbon-oxygen interaction gives this carbon a slight positive charge. This carbon-oxygen bond further increases the slight positive charge. So we see that the attack of the negative hydroxide ion on the positive carbon atom is consistent with what we know about bond polarity. Now we have proposed a mechanism that is consistent with what we know about the reaction. Let's devise an experiment which will further test our assumptions. Suppose we have an ester that is just like methylbenzoate, except that it has a methyl group substituted on each side of the ester group. These additional methyl groups would not appreciably alter the polarity of the carbon atom. Therefore, we might expect this ester to react in a manner identical with the original ester. You recall our proposed mechanism involves the hydroxide ion forming an intermediate molecule. But the bulky methyl groups interfere. The intermediate molecule is difficult to form. Reaction should seldom occur. If our proposed mechanism is correct, the hydrolysis of this new ester, methyl 2,6-dimethylbenzoate, should be much slower than the hydrolysis of the original ester. We'll test this idea by heating the new ester, methyl 2,6-dimethylbenzoate, in the presence of aqueous sodium hydroxide, repeating the original conditions. After stirring and heating for 8 hours, no detectable reaction has occurred. There are still 2 layers. This experiment also fits our proposed mechanism. Since no other suggested mechanism fits all our observations, we assume the proposed mechanism is the true one. Seemingly, these bulky methyl groups have greatly hindered the reaction. The steps we have followed of knowing the reactants and determining the products, exploring the path of each atom involved, checking our suggested mechanism against known bond polarities, and exploring the effect of structure on the reaction are typical of the methods used in determining reaction mechanisms.